Welcome to the Mechatronics Revolution, Fundamentals and Core Concepts. In this lesson, we'll talk about H-bridges and motor driver circuits. The objectives of this lesson are to describe the need for motor driver circuits when we build a mechatronics device. We'll explain how H-bridges work and how we connect them to microcontrollers. And finally, we'll review the specifications of several typical H-bridge integrated circuits. A mechatronic device typically has one or more high-power loads. And these loads are things like motors, LEDs, solenoids, servos, etc. Now, we can't switch these loads on and off directly from a microcontroller output pin in the sense that we can't drive them from an output pin. So these loads will draw too much current for us to source that current directly from the microcontroller. And likewise, we can't sync the current through these loads into the microcontroller output pin. So because we have a low power device, a logic level device connected to a high power load, we'll use a motor driver circuit or an H-bridge as the interface between the logic level device and the motor or servo. A simple motor driver circuit can be built from just a few components, in particular a power MOSFET, a diode, and a battery. And we can see a circuit schematic here of a simple motor driver circuit. Looking at this simple circuit, we can see we have a MOSFET, a flyback diode, as well as the interface VIN for our microcontroller, and the interface for our power source VDD, where we're going to drive our motor. So looking at the components here in more detail, first we can see we have the power MOSFET, and into the gate of the power MOSFET we have our microcontroller output logic voltage, so VIN. VIN is either going to be 3.3 volts or 5 volts depending on the model of the microcontroller we're going to use. We can also see that our motor terminals hook into this circuit on both sides of the flyback diode. And we've talked about the need for a flyback diode in this type of circuit in previous lessons. We can also see the interface for our battery. So this is the type of circuit we might build to activate a motor and interface it with a microcontroller, where the microcontroller is used to turn this motor on or off. This diagram now will show where we actually place the battery, or where we place the brush DC motor and the microcontroller. So we have our output pin of our microcontroller is going to be hooked to the gate of our MOSFET, and then the brush DC motor is going to be placed across those leads right across the flyback diode. When the logic on our microcontroller output pin is high, that's going to turn our MOSFET into saturation and allow current to flow through our motor and turn it in one direction. Then when we set that logic value low on our microcontroller output pin, that's going to turn our MOSFET off and no current's going to flow through the motor, so it'll stop running. A couple of things to note about this circuit. First, in this configuration, the motor, we're only going to be able to turn the motor on at one speed. So this is kind of a logic level circuit in the sense that it only has a binary operation. It's either in saturation or it's off. When it's in saturation, we'll see a voltage drop across those motor terminals of about VDD. But we won't be able to adjust that value in any way, so our motor's only going to turn at one speed. Likewise, it'll only turn in one direction. So we can't, with this type of circuit, reverse the voltage across the motor and allow it to turn in the opposite direction. So this simple driver circuit is really only good for turning on a motor in one direction at one speed. So that brings us to the concept of an H-bridge drive. An H-bridge is a typical integrated circuit that we'll use to switch the direction of current through a motor and allow it to turn in both directions. We can see a schematic of an H-bridge circuit here. Essentially, an H-bridge consists of 4 switches. The way this circuit works is we hook the motor terminals as shown across these switches here right in the middle. And we apply power to the H-bridge at the positive V up top and ground at the bottom. When we close switches 1 and 4, and we open switches 2 and 3, that'll allow current to flow through the motor in one direction and turn it in one direction. To flip the direction of the motor rotation, we'll then open switches S1 and S4 and close switches S2 and S3. Then current will flow through the motor in the opposite direction. And now we have a way, just by manipulating these switches, to turn the motor in one direction or another. The reason we call it an H-bridge is that the circuit schematic kind of looks like an H. Now, real H-bridge circuits are not made from mechanical switches. They're built from transistors, diodes, and then other components like logic gates. And the transistors act as the switching elements. So these are solid-state switches, not mechanical switches. The thing about transistors is that they have very fast switching times in the nanosecond range. So we're able to switch the direction of current through this motor extremely fast. This is a typical schematic of an actual H-bridge integrated circuit. And we can see that we have our transistors in the middle. So these are 4 MOSFET transistors in the middle of this H-bridge, as well as the other type of logic components, the logic gates, which kind of surround those MOSFETs. And that allows us to change when we input logic signals. It allows it to turn 2 switches on and 2 switches off, like we mentioned in the last slide. The final thing to mention is that if you look closely, not only do we have these 4 internal MOSFETs that act as these 4 switches, but we also have flyback diodes across each of these MOSFETs. So we don't actually have to incorporate flyback diodes when we interface with a motor. So that's very convenient when we use an H-bridge to drive a motor, is that we don't have to worry about things like flyback diodes. Here's a little bit of information about a typical motor driver integrated circuit, the DRV8840 available from TI. So this is an integrated H-bridge circuit, and it's made to drive brush DC motors as well as stepper motors, and it only costs a few dollars, so it's a relatively cheap component. We can see the schematic of how you connect this H-bridge motor driver to a microcontroller, which is labeled just controller in this diagram. So what we do is we connect the enable line to our microcontroller, and that's really going to be used to switch our motor on and off. So that enable pin is really just a digital input. We can send a logic high or a logic low to turn the motor on and off. The phase line is connected to another microcontroller output pin, and that's used to set the direction of rotation. So when we set that to 1 or logic high, then the motor will rotate one way. When we set phase to logic low or 0 volts, that'll set the direction of rotation the opposite direction. Now there's a few other lines that you can connect as shown in the diagram for more advanced functionality, but from a simpler standpoint, all you really need are those 2 output lines, the enable and phase lines. So with 2 connections, 2 wire connections between the microcontroller and the H-bridge, you can turn the motor on as well as switch the direction. Also important to note, some typical specifications for this type of motor driver are shown at the bottom. We have the maximum continuous motor drive current. So that's the maximum continuous current that you can put through this H-bridge to drive your motor. So if our motor is going to continuously draw less than 5 amps in operation, well, that's fine. If it's going to continuously draw more than 5 amps in operation, well, we need to get a different H-bridge. Likewise, we can't power our motor with anything greater than 45 volts. And finally, those digital inputs, the enable and phase lines, should be at either 3.3 volts or 5 volts. It can handle either one, and so you have a lot of flexibility in the microcontroller that you use. Finally, this internal circuit diagram on the right just shows a little bit about what's inside the H-bridge, and in fact, it looks very similar to the last slide. We can see our 4 MOSFETs as well as our internal diodes. Let's take a look at an example circuit setup here where we're using a microcontroller, specifically our MSP432 Launchpad, to turn on a motor in 2 directions. So the main components we have here are our Launchpad microcontroller, we have our motor, we have a battery, and we have a breadboard, which is containing our our H-bridge integrated circuit right here, and this is the TI L293 H-bridge. And then the only other components on this breadboard are 4 flyback diodes you can see right here. Now the H-bridge has flyback diodes incorporated in it, but we also include flyback diodes just to protect the H-bridge itself. And so you can see these are the main circuit components we have on the board. Now driving the H-bridge, we need 2 digital logic inputs. One input, when that input goes high, it's going to turn one direction, and then another digital logic input where when that input goes high, it turns the other direction. So these 2 digital logic inputs are essentially the direction pins. And you can see for this H-bridge setup, those 2 pins are driven by the blue and green wires, which go right to general purpose input-output digital logic pins on our microcontroller. So we're going to drive the direction of this motor from these 2 digital logic pins. A couple other things to note. First, we've connected a common ground between our microcontroller, this black wire, and our breadboard. So that black wire is our common ground hooking in right here. We also provide a power to the H-bridge via this 5-volt output on our launchpad board. Finally, this battery plugs in on this side of the breadboard, and that battery is going to be used to drive the motor. And so essentially this H-bridge kind of spans the gap between the low power side of our circuit and the high power side. So if you look over here, this is our digital logic coming from our microcontroller on this side of the board. This is the low power side of the board. And then over here, we have our high power side of the board. We have our motor and our battery plugged in here. So now that we've seen kind of the setup for this circuit, let's take a look at the software that will drive it. So this is some software that I've written to drive the MSP432 microcontroller that will allow us to turn the motor on and off in both directions. Now we're not going to go through the software line by line in detail, but essentially what we're trying to do is design the program so that when we push one of our input buttons on our launch pad, the motor turns in one direction. We push that same button again, the motor turns off. And then if we push the other button on the microcontroller, the motor turns the other direction, and so on. We'll use interrupts to do this, and we'll talk more about interrupts later on in this class. To get things set up, to go through the major steps at least, we set up these switches or these digital inputs that will allow us to turn the motor on and off. So these are our switch setups. Those are the functions we call to set up our switches. And then we configure our digital output pins. And these pins on pins 2.4 and 5.6 are the pins that run those blue and green wires that are going to drive the H-bridge. Going down to the bottom of our program here, this is what we call an interrupt handler. And this function is going to get executed whenever we push one of the buttons. And so what happens here is when we push one of the buttons, we will toggle the digital logic signal on one of our pins. So on either pin 2.4 or 5.6, we'll toggle those pins to turn the motor on and then turn the motor off when we press it again. As the final part of this demo, let's take a look and watch this circuit work. So we've uploaded our code that we just saw onto our microcontroller. And now all we have to do is press one of these buttons here, either the front button or the back button here, and we'll see the motor turn in different directions. So let's press the first button and we see the motor rotating. We push it again and it stops. And then we press the button on the other side of the microcontroller, we see the motor rotate in the other direction. So this is a simple H-bridge setup that allows us to turn the motor on in either direction with digital logic and just using these buttons as inputs. Finally, let's look at some example H-bridge integrated circuits. First, before looking at some of the specifications, I want to note that when we drive a load using an H-bridge, the load current passes through the H-bridge. So not only does it pass through the motor, but it also passes through the H-bridge, and that's going to cause those transistors to heat up. So we should make sure that H-bridge has a sufficient power dissipation rating for the load that we're planning to run. Now, many spec sheets will give you an equation for how to calculate power dissipation for your H-bridge depending on the load you're using and the voltage that you're supplying to your load. And you can use that power dissipation equation to compute how much power is going to be dissipated, and then check that that H-bridge integrated circuit is sufficient for your application. But you should understand that these motor driver circuits and the H-bridge, they are going to heat up when you operate them, and you might need to put a heat sink on them in order to keep them cool enough and make sure they don't burn out. A couple of typical H-bridge models are listed here, and we can see that two of the key specifications are the maximum current that you can put through this H-bridge. So for instance, 5 volts or 1 volt, or 5 amps, 1 amp, or 4 amps. And then finally, the supply voltage range that we can use to power our load. And typically there's a very wide voltage range, and a typical motor might require 12 volts or 20 volts or even 5 volts. And so a lot of these H-bridges will support really any of those input voltages to our motor. To summarize what we've learned in this lesson, the purpose of a motor driver circuit is to allow us to switch a motor or some other type of load on or off from a logic level device. We can build a simple motor driver circuit from just a MOSFET and a diode, and we have to make sure that our MOSFET has an appropriate power rating. H-bridges are used to switch a motor on in one direction or another, and they consist of transistors to act as solid-state switches, diodes, and then internal logic gates. Finally, H-bridge inputs can be driven by only 2 or maybe 3 microcontroller digital output pins.